Hello and welcome to JHEP's lesson on shapes of molecules suitable for OCR AS Chemistry Unit 1. EdXL and AQA, I think you do this so you can have a listen in, but I don't think it goes into as much depth as you need. So the first thing we should know is the Electron Pair Repulsion Theory and the valence shell electron pair repulsion. Basically, the first one tells us that we've got electron pairs in covalent bonds. We've got electrons sharing with each other. We've got electron pairs, and what they do, if there's more than one of them, they would repel each other, and they will repel each other as much as they can. And those are the two things that you just need to learn about the electron pair repulsion theory. That electron pairs, okay, you need to remember the pairs bit. Electron pairs repel each other. Even though electrons do repel each other, but remember, they will not repel each other when they are swapped. So when one is going down and one is coming up, they don't repel each other. They like that, okay? And that's what forms the electron pairs. So they repel each other as much as possible. And the valence shell electron pair repulsion theory is just, well, maybe not be a theory. Well, it is theory. It just predicts. We can use that to predict what the shape of molecules are, because we will be looking at molecules later on, you know, and we can use this theory to find out what the bond angles are and how it should look like. So when we look at the first one, we've got beryllium chloride. Now we should know that beryllium is Be and chlorine is Cl. So if we have a look at the periodic table, ptable.com, if we look at over here, beryllium, that's in group 2, so it's got 2 electrons on its outer shell, and we've got chlorine, and it's got 7 electrons on its outer shell. Chlorine needs 1, so beryllium gives it 1, because beryllium wants to get rid of its electrons, and chlorine wants to gain 1. But beryllium still has 1 more left, so what do? We bring in another chlorine. Okay, and happy days, everyone's happy. So 1 electron goes to the chlorine over here, and 1 electron goes to the chlorine over here. So the formula for that is BeCl2. Okay, this is ionic bonding, by the way, but when we've got shapes of molecules, it's actually covalent, and that's what confuses people a bit. The reason why I did it like this is because I would like to show you how to actually write down the formula of beryllium chloride, because you can't write BeCl because that would make this wrong. So we've got BeCl. I'm guessing that beryllium chloride can be bonded ionically as well as covalently. Someone please correct me if I'm wrong, but that is the general gist here. And the reason why I think that is because beryllium shares 1 electron with chlorine over here, and it shares 1 electron with chlorine over here. To make it a bit clearer for you, I'm going to label chlorine red and beryllium's blue, okay? Cl. And this is covalently bonded. This is all covalently bonded, by the way. Now, using the electron shell repulsion theory, we know that this is 180 degrees. The bond angle is 180 degrees. Now, imagine this. Imagine that you had your arms spread out wide, and you've got. How would I explain? No. Imagine that you've got your arms above your head. You've got your hands above your head, and your hands are these electron pairs. Now, for them to actually repel each other, they're going to repel each other all the way down till they are as far away as possible. And that is 180 degrees. If it's 181 degrees, they still have that chance of repelling each other even more. So it goes back to 180 degrees. So this bond angle is 180 degrees. And this shape is called linear. Okay, just like linear on the graph and linear in maths. We'll be talking a bit about maths, by the way, so get your maths hats on. and we've got two bonded pairs. Okay, these are called two bonded pairs. These are called bond pairs because these electron pairs are bonded with chlorine. So that's the first thing for linear for linear molecules. The next one is BF3. If you look at ptable.com, we can see that it's boron fluoride. Sorry about that. Now, imagine we had BF2. Okay, just imagine, for all the chemists out there, don't worry. I know this is wrong, but just bear with me. So we've got BF2. Okay, I know this is wrong. I know this is wrong. Now, we add the other bonded pair onto boron, okay, to make BF3. Now, this is an extra force. This is an extra electron pair, which is actually pushing these two electron pairs closer to each other, even though they're reluctant to. These are really antisocial people, and trust me, you probably will be in the month of May and January. But they are being forced to be pushed together even more. So they end up like, let's draw it very quickly. They're going to end up like this. Okay, they're closer together, and the bond angle decreases from 180 to 120 degrees. So the bond angle for this is 120 degrees. 120, 120, 120. This shape is called trigonal planar. And this is because if you place it on a sheet of glass in front of you, okay, if you place it on a mirror in front of you, it would actually stick to the mirror. Okay, you can place it flat on the mirror. That's what it means, a trigonal planar, and that is why these angles add up to 360. This is also planar, okay, because if you stuck it on the mirror, if you stuck this on the mirror, it would actually just be flat there, and these add up to 360 as well. 180 makes 360. So that's what trigonal planar means, and there are three bonded pairs. The next one is CH4 or methane, if you do module 2, because you will learn a lot about methane, so get used to it. So imagine again, I've got CH3, I know it's wrong, CH3, okay, H, okay, and they are 120 degrees. Now another bonded pair comes along, which makes CH4, and then pushes this even more closer together. They are reluctant to do it together, but now instead of actually doing it on the 2D way, they're actually finding different ways to repel each other. So now they're going to do it on a 3D way, on an X, Y, and Z axis. I know this is pretty mind-boggling, but let's just come back to that. So this shape is called tetrahedral. Okay, that's the first thing, tetrahedral. And the bond angle has gone from 180 to 120 to 109.5. 109.5. And as you may know, if you are a great mathematician, you'd find out that these don't add up to 360. Why? Because they are not planar. This is not tetrahedral planar. There is no such thing as a tetrahedral planar in AS Unit 1 level chemistry. No, it's actually put in a way that would not be able to just stick flat on the mirror in front of you. Okay, even this is wrong, because this is suggesting that we are on the planar wavelength here. No, it would actually, if you place it on the mirror, if you place it in the mirror, you'd find out that one of these would be coming towards you, another would be on the mirror itself, and the other one, the other hydrogen atom will be behind the mirror. Okay, so it would actually look like this. CH. Then we've got H here. We got a H here, and you got a H here. Okay, you might be wondering what these are. These are symbols. These tell us the location of the hydrogen atoms relative to the carbon. This tells us how this looks like without drawing it in a 3D way. So this wedge, they're both wedges, but this wedge tells us that the hydrogen is behind the mirror. Okay, it's behind the glass mirror. And this is telling us it's coming towards us. This hydrogen is coming towards us. It's in front of the glass mirror. This is on the glass mirror, and this is on the glass mirror as well. Okay, you do need to know that. So the bond angles are 109.5. 109.5. This is a must know. You need to know the tetrahedral angles and the linear and the trigonal planar as well. So that's 109.5. Also, there are 4 bonded pairs. Whenever you get the 3-mark questions on the OCR test, make sure you mention how many bonded pairs there are and how many lone pairs there are. But let's come to that later. Okay, I call it a 3D shape, even though all of them were 3D shapes, just because this is coming behind the mirror and this is coming in front of the mirror. So the next one, if you just think, oh, and also we've got SF6. I'm just going to quickly draw it for you. It's going to look like that. And this. Remember, this is telling us it's coming towards us. Sorry, it's a bit dodgy, but. And this as well. There. Okay, and one below. Sorry, it's supposed to be F. It's supposed to be fluorine. Sorry, F. Okay, it's in your book anyway. It's in the OCR chemistry book anyway, and that's an octagonal shape. Octahedral is an octahedral shape. I keep on getting it wrong. And the bond angles here are 90 degrees. Okay, these are coming. It's a bit like Beyblades. It's a bit like those things that you spin around on the tables. It's got that 3D kind of structure. So the next one is we've got to think about is lone pairs. You might not know what lone pairs are, but lone pairs are the even more depressed version of, not depressed, antisocial version of the bonded pairs. These lone pairs will actually repel the bonded pairs even more by 2.5% degrees. Sorry, it will repel the bonded pairs 2.5 degrees more than the bonded pairs will do. Okay, it sounds a bit confusing, but let's crack on with it. So we've got NH3, and that is ammonia. You need to know that as well, not just for this, but for all of chemistry. So we've got NH3. Let's pretend that this is actually no. Let's not pretend that. Let's pretend that it's NH3. 1, 2, 3. Sorry, again, this rubbish designs. NH3, and we've got the bond pairs here. We know that. Let's pretend that this is a bond pair. This is a bonded pair. Okay, so we've got a tetrahedral structure here. Okay, and we know that the tetrahedral structure is 109.5. We replace this with a lone pair, and we know lone pairs repel 2.5 degrees more. So 109.5 minus 2.5 degrees will give us 107.0. So the bond angles here are 107 degrees, and this is because the lone pairs repel more than the bonded pairs. This is another thing you need to write in your 3-mark question in your test paper as well. You need to write that lone pairs repel more strongly than bonded pairs. And that's why we've got this angle here of 107 degrees. Not obviously, but this is called the trigonal because, again, 3 bond pairs. Trigonal pyramidal. Okay, because if you put this on, the piece of paper, it will stand up and look like a pyramid, just with a big blob at the top. So this is trigonal pyramidal. the bond angle is 107, and there's 3 bonded pairs and 1 lone pair. You do need to write 3 bonded pairs and 1 lone pair in your 3-mark questions as well. When it asks you to predict the shape of a molecule, you do need to write that, and you need to write lone pairs. If you're Edexcel, you need to write. I think it's the bond-to-bond repulsion is no. You need to write the lone-to-lone repulsion is more than the lone-to-bond repulsion, which is more than the bond-to-bond repulsion. Correct me if I'm wrong, but it's a really long thing like that. You should check your book, because that is probably wrong. Okay, so you need to for OCR, you're just lucky. So you got 3 bond pairs, 1 lone pair. Lone pairs repel more than bonded pairs, and you end up with 107 degrees. The next one is H2O, our famous candidate, the water. You do need to draw the lone pairs. Maybe not on this molecule, but it's imperative that you draw the lone pairs. Remember, oxygen is in group 6, okay? It's in group 6 over here. So that means it's got 6 electrons on its outer shell. 1, 2, 3, 4. And one of the electrons are... let me just do this. One of the electrons are being shared. It's being shared with the hydrogen. Hello, hydrogen. And another electron is being shared by another hydrogen. Hello, hydrogen. So we've got 2. Again, this is the wrong structure, so don't copy it down. So, yeah. So yeah. That's what I wanted to say. Now imagine that these were bonded pairs. Let's get my black pen. Imagine these were bonded pairs. This will be a tetrahedral structure, because there will be 4 bonded pairs, and that would be 109.5. But since these are lone pairs, not bonded pairs but lone pairs, they will repel by 2.5 degrees more each. Okay, and since there are 2 lone pairs, they will repel by an incredible 5 degrees. So therefore, the molecule will not look like this, but actually it would look like this. And please remember to draw the lone pairs as well on either side, would be nice. And 109.5 minus 5 degrees, that will give us 104.5. And this is how you calculate it, because I find it difficult to remember all of these shapes and molecules. Also, this is called bent. This is a bent molecule because it's bent. It's not gay, it's just bent. So it's 104.5. This is the way to calculate it. The only things you need to remember is that the linear is 180, trigonal planar is 120, and tetrahedral is 109.5. You can calculate what the trigonal pyramidal, and you can calculate what the bent angle is for them. So that's bent 104.5, and what was I missing? 2 lone pairs, 2 bonded pairs. Okay, this, I would imagine that this is like a person with 2 legs sitting round, so you can draw them. Yes, you should be able to draw them as a planar. So this is planar. Okay, you can say bent. I don't think you can say bent planar. Just say bent or non-linear or V-shaped. So the next one is CO2. So you've got the carbon here, and we've got, oh, sorry. Actually, no, I am right. And we've got these double bonds. You do need to know that these are double bonded because carbon has got enough electrons and oxygen has got less electrons, should I say. No, it's got enough electrons to actually share again. Okay, because oxygen has got 6 electrons. 1, 2, 3, 4, 5, 6. It shares 1 with carbon, so that makes 7, and it shares another one with carbon, so that makes 8. And it does so on both sides. But you should know that without me even saying. and this angle is 180 degrees. Although you've got 4 bonds here, since they are bonded to the same atom, they will not be repelling each other in that way. In actual fact, we've got different ways. They've got different orientations, these bonds, because they've got a sigma bond and the pi bonds. We've got electrons flying all over the place between these, and we've got electrons just staying there. But that's for unit 2, so don't need to worry about that. If you are doing unit 2, you do need to know about the difference between a sigma and a pi bond, especially for electrophilic substitution. So this is 180 degrees. I know it would sound like a whole load of nonsense to unit 1, but when you do unit 2, you'll thank me. So this is CO2. There are it's linear. It's still linear, and the properties are still the same. Now, when we've got a molecule such as NH4, and we've got 1, 2, 3. I know this is wrong because one of them should be on the planar, one of them should be coming towards me, and the other should be coming back at me. Trust me, practice makes perfect. If you keep on practicing it, it will make perfect sense. So we've got H, we've got H, we've got H. In NH3, we've got a lone pair, right? But what about if that electron were to just move on to someone else? Okay, it got tired of being a depressing lad, and it just moved on to the next available atom which needed an electron. Okay, so here's an electron. We've got an electron here, and then hydrogen is like just coming along the place, you know, and thinks, oh, I need an electron. Oh, let me just bond with this because this nitrogen needs an electron. I need an electron, so let's covalently bond. And we've got NH4. Now, nothing changes. You might just need to draw, I know that's horrible, you might just need to draw the plus at the top, but nothing changes. It is a tetrahedral shape. Okay, when I say nothing changes, I mean as in the molecules do move around, but it's less repelled against each other. So instead of it being 107 degrees, it's relieved itself by 2.5 degrees, because remember, this is a bonded pair, not a lone pair. So it's 109.5, and that is a tetrahedral structure. 109.5, and it's just exactly the same as your normal tetrahedral structure. Okay, this is an ion, by the way, that's why we put that there. And that is it for shapes of molecules and ions.